So the first one on stage is Stefano Forti, and the stage is yours.
Thank you. So let me try to share my screen. Okay, great. Should work by now. Yes, right? Can you see it?
Perfectly. Go on.
Great. So good afternoon, everyone. I'm Stefano Forti, and I'm part of the Service-Oriented Cloud and Fog Computing Research Group at the Department of Computer Science, the University of Pisa. And today I'm going to present you this work about the green application place of multi-service applications in the Cloud-IoT Continuum. So, as we all know, we are assisting this softwareization of basically everything from smart factories to pizza deliveries to virtual and augmented reality, passing through telesurgery. And of course, this evolution in applications is accompanied by an evolution in the infrastructures. So while most of the infrastructure we are currently using exploit IoT devices in combination with cloud nodes, next generation infrastructures, which are spread along this cloud IoT continuum, will actually make use of edge and fog nodes, which are closer to the end users or to the device which produce and consume data. And all this continuum of computing, storage, and networking actually is composed of thousands of cloud and IoT nodes that are pervasive, distributed, and heterogeneous in nature. So we have very powerful devices and very, very small devices, which can be personal devices or battery-powered ones. And all these produces a lot of idle computing power, which is all around us, which could be actually exploited to improve on energy efficiency of application deployments, of the deployments of the application that we have seen before. So the motivation of this work resides in the fact that the energy demand for information and communication technology could reach 14% of the total worldwide footprint by 2040. And so the question that we are trying to address is how can we make software engineering green or more green and sustainable? And if we consider the life cycle of an application, we have the design phase, the development phase, and the deployment and management phase. And basically, a lot of literature address the problem of embedding sustainability in the design phase so that the computation is greener and more sustainable, while less work has considered the deployment and management phases, which constitute the longer part of the life cycle of an application, hopefully. So in this work, we really focused on proposing a methodology and a new prototype tool to assess and improve how green and how sustainable deployment of an application can be. And the problem we consider is more specifically the one that considers having a multi-service application to be deployed on top of a cloud IoT infrastructure, so to have all its requirements satisfied by the hardware, software, and IoT capabilities in the infrastructure, but also by the end-to-end latency and bandwidth that connects different nodes, while balancing between carbon emissions and operational costs that oftentimes represent very contrasting objectives. So in our previous work, we have proposed some declarative methodologies that are able to determine placements that satisfy the hardware, software, IoT, latency, and bandwidth application requirements, while determining the placement of each application service on top of a cloud IoT infrastructure. And today I'm going to present an extension of these methodologies, which is still declarative, which is still implemented in Prolog, that supports the cost, energy, and carbon-aware application placement in cloud IoT setting. And we have prototyped it in Prolog, as I said before, and it's open source at the link that you see on screen right now. So the idea is that we can model very simply multi-service application. So for instance, this is an application that is capable of managing the lights in a public space like a museum or a street by exploiting a video footage from a video camera and the lights hub to actually manage the intensity of the light that illuminates the public ambient that we're considering. And this lights driver service, which requires 2 gigabytes of RAM and Ubuntu available on the deployment node, interacts with a machine learning optimizer service that runs thanks to a GPU, has different hardware and software requirements, and required that the lights driver is able to stream video with at least a 16 megabit per second and at most 20 millisecond latency on the supporting end-to-end connection. And it requires that the ML optimizer is capable of streaming back the results of its computation to the lights driver with a maximum tolerated latency of 50 milliseconds and at least half megabyte per second of bandwidth. So very, very easily, we can transform this into Prolog and see all the power of our declarative specification of the input for what concerns the application model. And here we have the application, which is made of an identifier and the list of services. And for each service, we have its identifier, the software it requires, the hardware it requires, and the IoT devices it requires. And similarly, for service-to-service interaction, we can have the two services that interact annotated with their maximum tolerated latency and minimum bandwidth requirement. Now we move to the infrastructure. And basically, we have a very simple infrastructure here, which is made of 3 nodes, a private cloud, an access point, and an edge node. And they show capabilities that are complementary to the requirements that we have seen before. So, for instance, the private cloud features 128 gigabytes of free hardware. It provides its user with Ubuntu, MySQL, and Python. And then they also interconnect with each other. For instance, the private cloud can reach out the access point within 5 millisecond latency on average and a bandwidth of 1 gigabit per second, and so on and so forth. And as before, we can actually have a very, very simple Prolog specification of the sketch above, which also include the total hardware available at a node. So for instance, in this case, the access point has 4 free gigabytes of RAM, but overall it has 6 gigabytes of RAM, which means that 2 of them are used. And this will be needed later on to compute the load of the node. And we also model the unit cost of hardware at that node with a simple cost predicate. So far, so good. Now we start talking about energy and how we account for sustainability and green aspects in this model. So the first thing we consider is the power usage effectiveness, which is a commonly used parameter to determine how effective a node is with respect to the energy it needs for computing and for tasks that are not directly related to computing, for instance, cooling or networking within a data center. And actually, the power usage effectiveness is the ratio between the overall energy for keeping a node working and the energy which is used for actual computation. So for instance, a PUE of 1.5 means that for every 1 kilowatt hour used for computation, the node requires another half kilowatt hour for non-IT tasks. And we simply express the PUE of the nodes that were sketched in the infrastructure before by this simple facts, binary facts, which involve the ID of the node and its PUE. Then the flexibility of our Prolog prototype allows to express arbitrary energy consumption profiles. So how much energy a node consumes based on its load, on the load of its hardware. And this function is usually nonlinear, especially in modern processors where we have a baseline consumption and we add to that consumption based on the current load. So we have this kind of predicates that can be specified and declared by the node administrators, where we have the node identifier N, the current load, and the energy consumption that is associated to the current load. And to see some examples, here we have 3 very different energy profiles for the 3 nodes that we have seen before. So we have the first 2 for the private cloud and the access point that increase logarithmically based on the current load, while, for instance, the edge node only has 2 modes. One that is when the load is less of 50%, which involves consuming 0.08 kilowatt per hour, and another one which is let's say a high load mode, which has a 0.1 energy consumption in kilowatt hour. And now the other important aspect to consider when we talk about energy is what powers our device. So our device can be the most efficient in the world, but if it's powered by a coal power plant, then it's producing a lot of CO2 emissions. And for different power sources, we have estimates of the emissions that they input in the air, estimated in kilograms CO2 per kilowatt hour. And so here we have a few examples that are taken from recent literature. And we actually model this different energy source mix by considering the different percentages of energy sources that power a node, still specified as Prolog facts. So the private cloud is powered by 30% energy coming from a solar plant and 70% energy coming from a coal plant, and so on and so forth. Okay, so here we have the specification of all the source mixes that we consider in our example. And now we show how it is possible to determine eligible placement according to our previous proposal, and how we extend our previous proposal to consider the ingredients that I've illustrated a few moments ago. So very simply, given a list of placement of services, the placement predicate will determine an eligible deployment P that meets all the software, hardware, IoT, and network QoS requirements in terms of latency and bandwidth of the application that we have seen before. And it does so by scanning the list of services, checking the requirements service by service, and checking the latency and bandwidth requirements of the last placed service with all the services that were placed before. So this is an incremental behavior that implements a fail-fast strategy. Every time we find a service that cannot meet the requirements on latency and bandwidth, we backtrack immediately. It is worth noting that this approach checks cumulative hardware requirements and cumulative bandwidth requirements, as these resources are actually consumed by a deployment on the infrastructure. And finally, just for the sake of the example, I showcase the node OK predicate, which checks for non-deterministically retrieves a node and checks for the currently considered service, all the software requirements, all the IoT requirements, and then the cumulative hardware capabilities. So now, given this let's say, building block, this first Lego block, we have GFogBrain that exploits them, the found placement, the determined placements, to estimate their energy consumption, their carbon emissions, and their operational costs. And it does so basically by finding all of them and one by one, and determining first their footprint by exploiting this footprint predicate that, given a placement and its hardware and bandwidth allocation, estimates the energy consumption and the carbon emissions. And let's dive deeper in this footprint predicate. Basically, it first retrieves all the deployment nodes and computes the hardware footprint. So the footprint, the estimated footprint that is produced by the fact that we decide to place a certain service S onto a certain node N, and also an estimate of the network footprint. So since communication exploits a lot of different routers and also computing devices within the cloud IoT infrastructure, it is also producing and consuming energy and producing carbon emissions. And so we have to account for this aspect as well. And then we sum the hardware energy, the bandwidth energy, and we also sum the carbon emissions due to hardware and the carbon emissions due to network communication and bandwidth. And eventually, going up here, after we have found all these placements, we associate to each of them their hourly cost. So we have, for each placement, the cost, the energy consumption, and the carbon emission. And we sort placements by increasing carbon emission, by increasing cost, and then by increasing energy consumption. Of course, by swapping suitably these first three elements in the tuple, we can get different sortings. So as an example, we have used a simple model to estimate energy and carbon emissions. I would like to stress that this is just an example, as the flexibility of our prototype allows to easily embed more complex or more sophisticated models to estimate both the energy consumption and the associated carbon emissions. So we use basically a simple formula to estimate the energy consumption of service S at node N by multiplying the energy profile. So we compute the current load. We look at how much load is due to the deployment of S onto node N, and we compute the energy by using the energy profile predicates that we have seen before that is actually consumed by node N to support the deployment of service S, and we multiply it by its power usage effectiveness. And this gives us the energy consumption of having service S deployed at node N, the overall energy consumption in kilowatt per hour. Based on these, we can actually exploit the information about the energy source mix to compute the carbon emissions, which are due to such consumption. And so we basically multiply the energy consumption for the linear combination of the percentages and the carbon emissions produced by the mix that powers the considered node N. And similarly, we can also estimate at a less fine grain the energy consumption and emissions which are related to network transmission. And in this case, basically, we know that this is the average energy needed to transmit 1 megabyte of data. And with some conversion, we can compute the energy that is required to transmit more megabyte, starting from the data that we have in the specification of our application. And then by using this magic number 0.475, which is the global, the average emissions of the energy we use daily worldwide, we can estimate, let's say, the emissions related to network transmission. So with all these ingredients, we can actually see what happens in our example. Just let me recall, we have this simple two-service application, and we want to place it onto this three-node infrastructure that has the let's say the IoT devices needed by the application. And we run gFogBrain, and we obtain two candidate deployments, two candidate placements, one that places Light's driver onto edge node and the machine learning optimizer onto the private cloud node, and the other one, P2, that places the ML optimizer onto the private cloud node and the Light's driver onto the access point node. So, and those placements are associated with the emissions they produce, with their hourly cost, and with their energy consumption in kilowatt per hour. And based on these, we're sure that P1 and P2 meet the hardware, software, IoT, and network QoS requirements of our application. And we can see that P1 costs €3 a month less than P2, but it produces 30 gram of CO2 per kilowatt hour more carbon. So actually, P1 is, I think there's a, P1, produces less carbon. Here it is. So we have that P1 costs €3 more a month, but produces 30 gram of CO2 less in terms of emissions, and consumes a little bit less in terms of kilowatt per hour. Now the decision is left to the application operator, so they can exploit GFogBrain to decide, based on their business-related constraints, whether they want to follow profit maximization, so minimize the cost, also considering the fact that they might perhaps have to deploy and maintain more than one application deployment at the time. So this €3 a month might become more and more, or to actually be green, so minimize the carbon emissions of their deployment, of their application placement. And of course, as this involves business-related constraints, we can propose both alternatives, but it's difficult to decide. It's actually an open problem how to balance, especially when there are many more deployments and many more placements to evaluate and assess. So to conclude, GFogBrain represents the first declarative attempt to determine eligible cloud IoT applications in a QS-aware manner, but also in a cost, carbon, and energy-aware manner. And being declarative, it is very concise. It is actually around 130 Prolog single lines of code overall. It is easy to understand and maintain with respect to procedural solutions that settles around the thousands lines of code. And it can easily accommodate different cost and carbon emissions models. So in the scope for future work, we have to extend this prototype with multi-flavored placement, which means that for each service that we aim at placing, we might have different versions that can be placed, which feature different requirements. Perhaps they're less demanding in terms of RAM requirements, with a almost functionally equivalent behavior. And a proposal in this sense is the osmotic computing paradigm. We want to actually assess different estimation formulae for what concerns the carbon emissions and the power consumption that we've seen before, to employ continuous reasoning to implement an incremental reasoning prototype that is able to handle just a small portion of the problem when it is needed to replace or to move application services, for instance, because the underlying infrastructure cannot satisfy their requirements anymore, or when we are exceeding the target CO2 emissions that we have set for our application. So this would speed up searching for a new placement. And finally, we really aim at assessing our proposals on real case studies with real application and over testbeds. And we have actually recently concluded an experiment of one of these federated testbeds that might be a good asset to exploit also for these purposes. So this concludes my presentation. I hope I didn't go too long, and I'm open to
just a bit.
Sorry about
it. So let's thank the speaker. Thank you, Stefano, very much.
Thank you.
And let's see whether the audience has any question. Both in the chat or in the question and answer section.
Okay. I don't see any in the chat.
So in the meantime, I have a question for you.
Okay.
So very interesting talk. Thank you very much. And as far as I understand, this is very tackled towards a very specific problem, right? And it is solved in advance. It is not solved in real time. So you solve any kind of instance in advance, and then apparently there is an implementation following one of the proposed solutions. Is that right?
Yeah, that's right. Currently, GFogBrain precisely target, let's say, a priori and offline decision making. And this is, of course, because of the fact that it can be very long. For larger scale problem instance, it might take minutes to find a solution. So it's something that we must first decide and then implement in the application deployment. but the extension towards continuous reasoning precisely go towards making these techniques applicable also online, as it allows to solve smaller instances of the problem in a quicker manner live at runtime while the deployment is running. So this is what we would aim to at tackling in the next future work.
Okay, I see a question from the audience, and as you can see, would negation and/or justification be useful in your use cases? From Joaquin Arias or Arias.
All right. So I think so. Negation can be really useful, especially if we want to also tackle some or include in the modeling some security-related properties. And for what concerns justification, we haven't thought about it, but it might be probably an interesting line to study and to include in some future research about these. So I don't know whether I've answered to the.
Okay, Joaquin, are you satisfied with the answer? Okay, cool. So since we got a little bit longer, and I think it's time to move to the second talk.
Okay, so
thank you very much, Stefano. Thank you for your